Chapter 15, Particle Kinetics, Impulse and Momentum. We will finish this chapter in one video. So let's see, we have finished Particle Kinetics chapter 13 and 14, and this is the final part of Particle Kinetics, Impulse and Momentum. Let's start with the concepts of impulse and momentum. What exactly mean by impulse and momentum? So momentum is mass in motion, and any moving object can have momentum. It means anything, anybody that moves has a momentum. Momentum definition is mass into velocity. Whatever object's mass and whatever the velocity, that's your momentum, normally given by letter P. So if you are traveling with a car, you have some velocity, you have some mass, your car has a mass, and collectively you will have momentum. Mass is constant, so as more velocity, more the momentum. If velocity is 0, then in that case you have 0 momentum. So momentum is very simple. Anything, any objects that is moving, let's say in straight line, it has a momentum, and normally it's referred as a linear momentum. If it is traveling along a curved path, then it is referred as a angular momentum. So that's your momentum. Mass in motion is nothing but a momentum. Now let's imagine, let's say that you're traveling on a road with your car and you skip a stop sign. Now you are in speed, let's say 40 miles per hour, and you have some momentum, mass into velocity, and you skip a stop sign and then another car hits you. And if that happens, your momentum will change. Now after the impact, the momentum will be different than whatever it was before. And that change in momentum is nothing but impulse. Impulse is normally given by definition F dt. That's the force of impact that you are having from another car in time dt, very short amount of time, half a second or less than that. That force into dt, that collectively we call it impulse. So momentum is mass in motion, and impulse is change in momentum. If something happens and because of that your momentum changes, that's known as impulse. So that's your impulse and momentum, some basic understanding about what exactly it means. So let's derive the equation for momentum. Now we know our second law, F is equal to ma. I can write this acceleration as a dv by dt. That's derivative of velocity. I can take this derivative of velocity, put it here in a, and if I do that, it will look something like this. F is equal to m dv by dt, and then I'm going to take this dt on left hand side. If I do that, that will become f dt, and that's nothing but our momentum. So here I have f dt is equal to m dv. That's nothing but impulse. Sorry, f dt is our impulse, and here I have m dv. Now I'm going to integrate it both sides. I have dt here, I have dv here. I'm going to integrate it both sides, and if I do that, I will get integration f dt is equal to mv2 minus mv1. So what we can see is that we have mv2, that is your final momentum, minus mv1 is your initial momentum, and then f dt is an impulse. So impulse is equal to f dt in time t1 to t2 is equal to mv2 minus mv1, and that's what we call it as principle of linear impulse and momentum. So all you have to remember is that final momentum minus initial momentum is nothing but impulse. So here there are two kinds of momentum, linear momentum and angular momentum. For linear momentum we use letter L. So here this part f dt, I'm going to call it I is equal to f dt, and this part I'm going to call it L. This is L2 final momentum, this is L1 initial momentum, and then if I write that, this principle will look something like this. This is the same equation, only written in different format. So I have impulse is equal to final momentum minus initial momentum. I is equal to L2 minus L1. Now in chapter 14, if you remember, we learned something called as principle of work and energy. Principle of linear impulse and momentum is similar thing. There are some similarities, there are some differences. What are similarities is that your impulse and your work done are associated with process. They need path followed, or whatever the process from 1 to 2, they are associated with it. Whereas your momentum L, and your kinetic energy T2 minus T1, change in kinetic energy here, or these kinetic energy T2 and T1, they are associated with state. This is essentially L2, L1, T2, T1 is a state, it's not a process. These are some similarities. What are the differences? This principle of work and energy that you learn in chapter 14 is a scalar equation. Energy is a scalar, so it is a scalar equation, whereas momentum, you need magnitude and direction both, and therefore it is a vector equation. So that's your principle of linear impulse and momentum, and slight relations with principle of work and energy. Now let's continue with our discussion with principle of linear impulse and momentum. Now what I am going to do that, this is our equation. I am going to take this mv1, I am going to take it to the left hand side, and I am going to rewrite this formula. So if I do that, what I get is mv1 plus impulse is equal to mv2. What does it mean? You have initial momentum, then you have an impulse, and because of that your momentum is changed. For example, you are driving at 40 miles per hour, you have a mass, you have velocity, and then you skip a stop sign and another car hits you. When another car hits you, that's your impulse. And because of that impact from another car, your momentum changes. So you have initial momentum, some event happens, and because of that you change in final momentum, and that's what you can see here. The object is moves, it has some initial momentum here, and then you have some impulse, some other force is applied on that object, and because of that final momentum changes. And that's how you can imagine this idea of impulse and momentum. Initial momentum, impulse, final momentum, and that's pretty much it. Now, important thing about this equation is, as I said before, this is a vector equation. It needs magnitude and direction, and as it is a direction, it will have three components. If I am operating in Cartesian coordinate system x, y, z component, then I will get three components, or I can write three equations for x, y, and z direction from this equation, and those equations will look something like this. This is impulse, that this is momentum in x direction, x force, and change in momentum in x direction, and that's what same thing with y, force in y direction, and then final y momentum, z direction impulse, z direction momentum initially, z direction impulse here, and final z momentum. So I can rewrite this depending on my coordinate system. If it is two-dimensional, then I don't need z, only 2 is enough. But this is the equation that I can resolve into three components x, y, and z based on the direction. Now let's do a simple problem, and let's see if we can understand how to use this principle of impulse and momentum. Now let's say we have this toy car here. Initially this toy car is at rest, and then what you are going to do is you are going to apply this 3.5 Newton force in this direction. And once you apply force, what we want to find out, determine the velocity of the car after 2 seconds. So initially the velocity is 0, it means it has a 0 momentum, and now you apply force, some force is applied for 2 seconds. And because of that, after 2 seconds, its momentum will change, and if you know the final momentum, you should be able to calculate velocity, and that's the idea. Initial momentum 0, force applied for 2 seconds, and then final momentum changes. If you know final momentum, you should be able to calculate its velocity. So if we draw a general free body diagram, it will look something like this. We have normal forces, or vertical forces cancel out, there is no additional vertical force. So here we have F 3.5. I'm going to take my x coordinate system, y coordinate system, x positive in that direction just for convenience. Now this problem you can solve it by two different ways. A method, something that you learn in chapter 13. In chapter 13, what you do is that you apply Newton's law. You have F forces in x direction equal to max, and then you have 3.5 here, you have mass of the toy car, and then you put ax, you calculate acceleration, and then you take that acceleration value, and then you use in chapter 12 equation, the kinematic equation, final velocity, initial velocity, acceleration into time, and then 2 seconds, and then you can calculate your answer. So that's your chapter 13 method. By using Newton's law and kinematic equation, you will get 20 meters per second. But there is a simpler way. Instead of 2 steps, we can use only 1 step or 1 equation with which we can do this problem. What will be the velocity after 2 second mark? And that's by using this equation. So what we have is only one equation: initial momentum, impulse, final momentum. Initial momentum is 0. The impulse force is constant 3.5. I'm going to take it outside of the integration. T1 to T2, 0 to 2. I'm going to solve this simple integration 3.5 into 2. That whatever it will come, 3.5 into 2 will be 7. And then mass into V. So I have a mass here. I'm going to take that mass, divide it in here, and then I'll get still same answer, 20 meter per second. That's what we got with chapter 13 method. So that will give you some general idea how this equation works. What we have is initial momentum, force applied, calculate final momentum, calculate velocity, and that's the whole game here. So instead of using two equations, we can use one simple equation and we can solve the problem. Now depending on problem what to do, but this is another way to get same answer that we got here. Then the next part is for the system of particles. So this here the equation that we apply is for one particle. So here we consider this entire object as one single particle, and then we apply this equation or this principle of impulse and momentum. But what to do if we have more than one particle, 2, 3, 4 particles? That's called system of particles. And if that's the case, we simply add those momentums and add those forces or impulses. So here summation sign, all the momentums, all the forces applied, and then you will get summation for final momentum. Now it's very difficult to get velocity of all the particles. So what we do is that we take velocity at the center of gravity. Instead of having velocities of all the particles, take the velocity of center of gravity. So we can write it as mvg1. So collective mass of the system or of all the particles, then velocity of that center of gravity, then force applied, that's your impulse, and then mass into whatever the final momentum, also that velocity of the center of gravity. And that's how we can do it for a system of particles. Now for some reason, when you use this equation for system of particles, you have lots of particles here in the system, and then what happens, for some reason, sometimes all the forces in the impulse, they cancel each other out. And if that happens, this force will become zero. For a very short period of time, if the forces, they cancel each other out, then this Fi will become zero. And if that happens, then what I can safely say is that momentum is conserved. It means that whatever your initial momentum will be equal to final momentum, because all the forces are, for a very short period of time, forces are cancelling themselves. And that's what we call conservation of linear momentum. If for some reason your momentum is conserved, then all the forces, they cancel each other out. If that happens, then that's your principle, that's your conservation of linear momentum. So let's do a problem and let's see if we can see this conservation of linear momentum. Now this is a solved problem from the book. What we have in this problem is a 15,000 kilogram boxcar. So this is a boxcar, 15,000 kilogram or 15 megagram, and this is another boxcar we have, slightly smaller, 12,000 kilogram. So this one is 15,000, this one is 12,000, this one is traveling 1.5 meters in this direction, this one is traveling on the same track 0.75 meters in opposite direction. And then as you can see, they are going to collide at some point. So what happens is that, let's say their collision takes place for 0.8 seconds. Let's assume that. Now what happens is that they have some force, they have some mass, so they will have some mass into velocity is my momentum. So it will have some momentum, it will also have some momentum. But at the time of impact, when the actual impact for very short period of time, the force of impact cancel each other out. And at that instant, when they get coupled for very short period of time, they are going to impact, and for let's say 0.8 seconds, they are going to couple each other for a short period of time. And they will act as one object. So instead of considering them two different things, for a short period of time, I can consider them as one single object like this. I can draw one single box, and then I can safely say that for that short period of time, the forces here, they cancelled each other, and then therefore net force is zero. And if net force is zero, I can safely say that momentum of this entire system after impact is conserved. So here, as I said before, if this force cancels out, then momentum is conserved, and that's what here we see. So here before impact, before these two have some momentum, and that will be here, and then it will have after impact, they will act as a one entity, and then they will have some momentum. So in the first part of this problem, what we want to do is that find out the speed of the cars just after coupling. So they are going to have an impact, and then for a short period of time they are going to couple, and at that instant when they are coupled, when the force is cancelling, I want to find its collective velocity of this entire box after impact. So what I am going to do, I know initial momentum, I know that momentum is conserved. It means whatever the initial momentum will be equal to final momentum. I am going to calculate this final momentum, and then based on that I can calculate this velocity of this system after the impact, and that's the problem here. That's your conservation of linear momentum. So before momentum I have initial momentum of A, initial momentum of B. I am going to write that down. Then I have here final momentum, that will be combined, masses are combined into V2. That's what I am interested in, V2. So I am going to solve this problem. Now here this 1.5 in this direction I am going to take it positive, here 15,000 MV, and then this 0.75 is negative in that direction, so I am going to put that negative sign there, and as because the direction is opposite, so negative, I have mass into velocity of this small boxcar, and then is equal to collective mass into V2. All we have to do is put these numbers in the calculator, and then you will see final answer 0.5 meter per second. What is mean? That they are going to have an impact, and for a very short period of time they are going to get coupled, force will cancel, and collective velocity of entire system is 0.5 meter per second, and that's it. It's very simple. That's what momentum is conserved. That's the first part of the problem. The second part of the problem says find out the average force between them if the coupling takes place for 0.8 seconds. What it says is that yes, there are forces cancelling each other out for 0.8 seconds. But what is the magnitude at which they are going to cancel? What is the magnitude of F for this one and this one? We want to find that out. And therefore, to do that, to find that magnitude, now I am going to consider only one boxcar because I want to know the value of F. So right now I am going to consider only one boxcar, and in this case now the momentum is not conserved because we are only considering one boxcar, and then we have to find out the F. So here what it says is that average force. Now when it says average force for 8 seconds, I can rewrite this F dt as F average delta t. So delta t is 0.8, F average I want to calculate. So this F dt will become F average into 0.8, and I am going to use that F dt here in this equation. So let's say boxcar A, initial momentum, then this force impact happens, and because of that its final momentum changes. And I have already final velocity V2, 0.5 meter per second. I already have that, so I can calculate this F average. So I am going to put that there. I have this initial momentum for A. Then force. Now in this case force is in this direction, so I am going to use that minus sign here. F average 0.8, and then final momentum. I have already velocity we calculated. Run these numbers, and then once you do that you will get final average value 18.8 kilonewton, and that's the problem. You can solve this problem by considering this boxcar. Now if you see here this boxcar, you can solve this problem by considering this other boxcar, and then at that time the force will become positive, but you will get same answer. So you can do that. If you want to practice, take this boxcar, instead of 12,000 here, whatever the velocity 0.75 here, and that will be minus, then here plus force average, and you do that, you will get same answer. So you can do this problem either way. You can do this problem with this one, either way you will get same answer, with which that force is cancelling itself, and that will be 18,800 Newton. Now let's move on to the next part, impact and coefficient of restitution. Now whenever two objects collide, there is an impact. We have one object with very high velocity, another object with zero velocity, and when they are going to collide, that's called impact. There are two kinds of impacts. One is a central impact and another is oblique impact. Central impact is a simple one. When the forces are in straight line, everything is happening in straight line, and there is no y direction force, let's say. So this is coming from x direction, this one is coming from x direction. This line of center of impact is also passing through center of gravity of these both objects. If that happens, I'm simply going to call it as a central impact. It's very simple. And then if it is meeting at an angle, if they are colliding at an angle like this one, this is coming from this side, this one is coming from this side, if they are colliding from an angle, I call it oblique impact. And these are two kinds of impact we have, central impact and oblique impact. What is the mechanics of impact? What happens exactly when there is an impact? So let's assume that there is an object A and there is an object B. Let's say object B has almost zero velocity or very low velocity, and object A has very high velocity, and therefore object A has very high momentum and object B has very low momentum or almost zero momentum, and that's your before impact. And now the impact begins, the contact begins, that's step 2. We have mechanics total of 5 steps. Step 1 before impact, step 2 impact begins. As impact begins, we call it deformation impulse. It means now the object begins to deform because of the high velocity. All that energy transfer will begin from A to B, and as the energy transfer from A to B is there is a deformation, that slight deformation of A and B that you will see. And then as this deformation begin, at certain point they will come to step 3 where you will have maximum deformation like this one. At that point the deformation is so high that after that deformation is not possible, and that's what the step 3 we call it maximum deformation. It means that this is still a process that almost all the energy is transferring to this object B, and that's your maximum deformation, step 3. Then you will reach at the point where now they are starting to take back its original shape. The most of energy of A has transferred to B, and now you have restitution impulse. It means that they are coming back to its original shape. It's very simple. So now you have restitution impulse, they are coming back to its original shape, and then after that you will have stage 5 after impact, in which all the energy of A has been transferred to energy of B, and because of that the velocity of B or momentum of B has increased, and velocity of A is almost zero or very low after the impact, and that's what you see here. That's your after impact, velocity of A very low, velocity of B very high. Before extremely, in step 1 A has very high velocity, in step 2, in step 5 B has very high velocity, high momentum. And these are the mechanics of impact. These are 5 steps that you will see in general when there is an impact. That leads us to something known as coefficient of restitution. Whenever this deformation happens here, whenever this deformation happens, that tells us something about this coefficient of restitution. What it means, what is this coefficient of restitution? It's simply the ratio of velocities. Coefficient of restitution is a ratio of difference in final velocities divided by difference in initial velocities. Of course, both object collide impact, they both will have some velocities before and after. So that's before, that's after divided by velocities before the impact. What exactly it means physically? Let's say I have a ball, that's body 1, and there is a floor, that's body 2. Now floor has zero velocity. So if for some reason coefficient of restitution in perfect world, if it is 1, the value is 1, then what will happen? If you drop this tennis ball, it will come at exact same height if coefficient of restitution is 1, but normally that's not the case. If it is 0.8, the coefficient of restitution here, if it is 0.8, then it will drop and it will come to 80% of the height. So if it is whatever it is, let's say this is a 1600, whatever 80% of that, it will come there if it is 0.8. If it is 50%, it will be half. If it is 0, if for some reason if E is 0, that's called plastic impact. It means that this will come down and then it will stay there, it is not going to bounce back, and that's what it means, that coefficient of restitution. So here coefficient of restitution is determined by experimentally between two colliding materials. So there are lots and lots of experiments. So these companies that makes this tennis balls or basketballs, they do these kind of experiments, and based on that they can find out what is the coefficient value of coefficient of restitution. Normally it is between 1 and 0. 1 is elastic impact, it's only in theory, it's not possible. And then there is a perfect collision where there is no energy loss at all. You can call it as elastic impact. It does not happen, it's only in theory. And then there is a plastic impact. It could happen. If you are using maximum loss of energy, all the energy is converted, in that case we can call it as a plastic impact. In that case this E is equal to 0, and that's what we call coefficient of restitution. There is a video, I think, on your blackboard slides. Make sure that you watch that video about this coefficient of restitution. Then what kind of problem we are looking at for this impact part? So if it is a central impact, normally the problem is that we have two objects colliding with a central impact, find out they have initial velocities, find final velocities, and that's the problem. So it's very simple. If that's the case, then what we can say, we can apply this conservation of linear momentum. In this case, if it is an x directional impact, central impact, then momentum is conserved. So we'll get this equation: before impact, after impact, momentum after impact. We have to find out velocities after impact. So that's one equation, two unknowns. We need another equation. And that's when we use this coefficient of restitution. Normally in these problems, E is given, use that value, and then you will have two equations, two unknowns. Solve these two simultaneous equations, and once you do that, you will get final velocities. And that's what you can do it for this kind of problem with central impact. And then we have problems with oblique impact. They are also very easy. Only difference is now that these two objects are colliding at an angle. When that happens, you have initial velocities, you have to find out final velocities, and we will see that in this problem. If that's the case, what you have to do is that first x direction momentum is conserved, apply this equation and coefficient of restitution, use this equation, these two equations, two simultaneous equations, two unknowns, you will get x velocity. Once you have x velocity, as far as y velocity is concerned, what you see is that there is no y directional force. It means whatever velocity of y direction velocity is going to stay same, and that's how you, once you know y velocity before, you can calculate y velocity after. It's very simple problem. Let's directly see the solve, if we can solve the problem. What we have in this problem is this object A is coming at 30 degree from this angle, this object B is coming from 45 degree at this angle. There are some velocities here. What we want to do is find out velocities after the impact, and then there is coefficient of restitution is given 0.75. That's your coefficient of restitution. Now our objective is to find out final velocities. So initial, as this is at angle, I have x and y coordinate system. I can resolve this velocity into x and y. So before impact, I have these velocities, I have numbers. Whatever the cos component and sine component will be x and y velocities of this one. So I have these four values. That will be 3 cos 45, 3 sine 45, and that will be 1 cos 45, 1 sine 45. I have these values. What I want to do is find out these values after impact, and that's the problem. There will be an impact, you have initial velocities, find the velocities after the impact. Very simple. So these four values I want to find out. For that, what I am going to do is that first I am going to calculate x directional velocities. For x direction, as this is happening around x plane, this is a line of impact along x direction, this one. The x momentum is conserved. So I am going to use conservation of momentum in x direction. I have one equation, two unknowns. I need to know this one and this one. So I am going to use then coefficient of restitution. Again, it's in x direction. So I have this x direction, line of impact is again x direction. So coefficient of restitution in x direction is 0.75. I'm going to take that value 0.75, put it here. I have two equations, two unknowns. I'm going to solve those two equations for two unknowns, simultaneous equations. It's easy, it should be. This is a solved problem from the book. To solve these two equations, two unknowns, and then you should get your final velocities. In this case, the final velocity, the x velocity of this one is 1.26 x velocity, and this one y velocity is 1.22 meters. So it's coming like this. That's your x velocity, 1.22 meter per second. And that's what you get. All you have to do is solve these two simultaneous equations. If you do that, you can find out x velocities. That's the first part. The second part, you have to find out y velocities. Now, when you do find out y velocities, what we see is that there is no y directional force. If we draw a free body diagram, what we see is that there is an x impulse. There is also x impulse. There is no y impulse here. And when that happens, when there is no y impulse, that y force is 0, and therefore, as there is no y impulse, whatever y velocity will be exactly equal to after impact. So y velocities before impact, after impact, they are going to same. It means 3 sine 40, 3 sine 30, and here 1 sine 45. Those are the velocities also after the impact. So that's what we do. whatever the velocities before impact, y velocities, they will be exactly same after impact, and that's what we calculate. VAY is equal to VAY1 is equal to VAY2. We use that and we can find out, and that's it. That's how you can find out final two velocities. So you can calculate x velocities and you can calculate y velocities. This one is a solved problem from the book. If you have difficulty in this thing, read the book, understand the problem from the book. It is very, very easy problem. Now let's do another problem. Now what we have in this problem is we have two objects, just like similar. We have oblique impact, two objects colliding with each other. Only difference now, they are colliding around this axis or around at 45-degree plane. So this object is coming from this side, this object is coming from this side, and they are going to collide at 45-degree angle. So here we have initial velocities, we have masses given, we have initial velocities 5 meters and 3 meters here. What we want to find out is final velocities and final direction. What are the final velocities? So first thing first, I'm going to take my xy coordinate system for convenience. I can have my x coordinate system along the line of impact. So this is my line of impact. Line of impact, it goes through center of gravity and point of contact. So center of gravity here, point of contact here, draw a line. That's called line of impact. I'm going to take line of impact around x direction here, and then y perpendicular to that. And then I'm going to have my x velocities and y velocities. So here, this is before impact, velocity is before impact, x and y velocity, whatever it will be. I'm going to resolve this velocity before that. That will be 3 sine 45, 3 cos 45. Here 5 sine 45, 5 cos 45, because the angle is 45 degrees. So this one will be 45 degrees. And I'm going to resolve these velocities before impact. So I will have numbers before impact. All I need to find out velocities after impact. So I know velocities before impact, sine and cos component of these velocities. I want to find out velocities after impact, and that's the problem here. Now for that, x direction component, we are going to solve this problem just like we did before. First we are going to have x component velocity, that velocity after x velocity after the impact, and for that what we are going to do is that we are going to have these equations here. Now as x momentum is conserved, this is the one equation that I'll get for x direction. I have these velocities. My objective is to calculate this and this velocity. I need one more equation, which is this one. Coefficient of restitution is given 1.5. So that is given. Now what I'm going to do is that I'm going to solve these two equations, simultaneous equations, two equations, two unknowns, and I can find out velocities after the impact. So here, before impact, velocities before impact are nothing but sine and cos component. That will be 3 sine 45, 3 cos 45 and 5 cos 45. So here these are the velocities, and as this one is in this direction, that will be negative direction, that will be, so that's why minus 3.45 meter per second, that's minus sign here because this is negative x. All I have to do now, if you have time, you can pause the video, you can do this problem. Take these velocities, put it here, here, and then you will get two equations, two unknowns, this one, this one, this one, this one. Solve these simultaneous equations, and if you do that, what you see is that velocities after the impact, that's x velocity after the impact, you will get here minus 31.11 meter per second and minus 275 meter per second. All you have to do is solve these simultaneous equations, and that's how you can calculate velocities after the impact. And then as far as y velocities are concerned, there is no y force. It means this y force is 0, and as y force is 0, what I can safely say is that y velocities are equal after the impact. So whatever the sine component of this one and this one stays same, and I can simply have that sine component here, 2.15 minus 3.4, that's your sine component. It is 45 degree angle, so it looks same. So that's your sine component here, and that's my velocities after impact. So now velocities before impact we have, y velocity after impact is going to stay same. So it will look something like this after impact. So we calculated this velocity, this velocity, this and this velocity. And if I apply Pythagoras and then direction vectors, I can find out exact direction of these two objects are going after impact. So this is going to come on this side, and then this will go like this with this velocity. Then this is going to come on this side, impact, and then this will go into this direction with this velocity. That's what I can find out what happens after the impact. That's it. That's your problem. Alright then, let's move on to the next part, angular momentum. The way we have linear momentum, same way we can have angular momentum. Linear momentum, mass into velocity. Angular momentum, we'll see. Now, if you remember from your static course, something called as moment of force. Moment of force is nothing but force into distance. So here, the more distance is there, less force I have to apply, and that's your moment of force, force into distance, given by F into D. So the movement around point O is F into D, force into distance. That's a scalar formulation. For vector formulation, I can write down, if I have position vector R, in that case I can have moment around point O is R cross F, and that's what I will get moment of force in vector formulation, R cross F. This one is a scalar formulation, this one is vector formulation. That's what you did in your static class. Now, angular momentum, just like linear momentum, let's say an object is rotating around certain axis. It will have a linear momentum, but as it is a curved nature, it will also have angular momentum, and that angular momentum I can calculate it as h O around point O, mv into d. So whatever your linear momentum into the distance from the center, you take that and then you will get mv into d. That's your angular momentum. It is also known as moment of the particles linear momentum. Moment of particles linear momentum. This is a linear momentum and this is into distance. Or other word is moment of momentum, and that's your angular momentum. So something traveling in curved path, that's your angular momentum. Let's say Earth is traveling around the sun, so that has an angular momentum, and we can calculate that angular momentum for planet Earth, and we will see about that. So that's called angular momentum, mv into d, whatever the linear momentum into distance from the center, you take that, you will get scalar formulation d into mv. If it is a vector, vector formulation is, if this is position vector r, then I will simply say r cross mv, position vector r cross mv, that will be simply, we call it as vector formulation. So what is the relationship between moment of force and angular momentum? So you learn moment of force in static course. What is angular momentum and what is the relationship? So moment of force in vector form is r cross f. We know that. Now I can rewrite this f in the form of Newton's law. So Newton's law is F equal to ma. A is nothing but dv by dt or v dot. So here I have F is equal to mv dot. I am going to take that mv dot and I am going to put it here. So here m will become r cross mv dot, and that's what I am going to write. Moment of force is r cross mv dot. Now if you look at the definition of angular momentum, r cross mv. This is the definition of angular momentum. Here we have mv dot, here we have mv. So what I am going to do, I am going to differentiate this one with time. If I do that, to look something like this, now here what we see is that this r dot here and then mv, v is nothing but distance upon time, that's again r dot, the derivative of distance versus time. So here we get that mv is nothing but r dot, so I can rewrite this one, and then what I can see is that as this v is nothing but r dot, this r dot and r dot cancel out and this term will become 0, and this terms become 0, it means that derivative of angular momentum will become r cross mv dot. R cross mv dot, exactly what I get here, r cross mv dot. It means that this part and this part is exactly same, so I can safely say that the relationship is moment of force is nothing but equal to derivative of angular momentum. And if when you solve the problems, this could help to understand when you have combination of moment of force and angular momentum, this relationship could help to understand overall what's happening with the system. So that's your relationship, moment of force is equal to derivative of angular momentum. Now let's see the principle of angular impulse and momentum. The way we have seen the principle of linear impulse and momentum, you are driving, you hit a car, your momentum change. So initial momentum, some event happened, change in final momentum. Same way, there could be the principle of angular impulse and momentum. Something is going around the curved path, an event happened, moment of force is applied, and because of that, that's called angular impulse. So this is angular momentum, you have angular impulse, and because of that, final momentum changes. So this one is angular impulse, so something is traveling around curved path, bam, something happens, there is a large moment force is applied, and if that happens, your angular momentum changes, and that's what we call principle of angular impulse and momentum, and that's it. Just like the similar to the principle of linear impulse and momentum. Then we have conservation of angular momentum. For some reason, all the forces applied at the moment, they cancel each other out. This MO, if this MO, moment of force, becomes 0, then what I can safely say that initial momentum of the system is equal to final momentum of the system. Here, that's what I can say, that this is a conservation of angular momentum. It means that momentum is conserved. So this equation is known as conservation of angular momentum. It states that from T1 to T2, the particle's angular momentum remains constant. So if we are traveling, if something is going around the curve path, there is a moment of force. However, that moment, all this moment applied on each other, it becomes 0. That summation of all the moment of forces becomes 0. If that happens, the momentum is conserved. And that's exactly what's happening with our planet. When our planet rotates around its own axis or rotates around the sun, when all these planets rotate around the sun, that momentum that we got at the beginning of the solar system, and that is still conserved after these billions of years, and that's why we can continue to rotate around the sun, continue to rotate around our own axis. There is no net moment of force is applied. If for some reason tomorrow, let's say there is a large asteroid impacts Earth, very large asteroid with very high force impacts Earth, in that case there will be incident, this moment of force will not be 0, and if that happens, the Earth's angular momentum will change. It means it could change the direction, it could change the velocity of how Earth rotating itself around itself. That could happen, but for now we don't have to worry about it, as everything is safe, as this moment of force is 0, as momentum is conserved. I can safely say again that this one is a conservation of angular momentum, that momentum of our Earth is going to stay constant for next foreseeable future or whatever billions of years coming forward. So that's your conservation of angular momentum. If it is a system of particles, if there is more than one particle, let's say all the star system flowing or rotating around the galaxy, center of the galaxy, then I'm going to uptake the momentum. Initial momentum is going to be final momentum. I'm going to just add summation sign, summation of all the momentums is equal to summation of all the momentums afterwards, and that's your conservation for angular momentum for system of particles. Now let's solve a problem, and let's see if you can use this principle to find out final velocities of the object. So what we have in this problem is, this is a car, it's traveling around a curved path, and when it travels around the curved path, there is a force applied. That force is 150 t square Newton. So this force is depend on time. Initial velocity of the car is 5 meters per second. The force is applied 5 seconds, and what we want to find out is velocity after 5 second mark. So car is moving with 5 meters per second. For 5 seconds, you apply this force, and because of that force, the velocity will increase. We want to find out how much. We want to find out what is its final velocity after 5 second mark. So for that, we are going to use this principle of angular impulse and momentum. So here, the car has initial momentum. Apply your force, you will get final momentum. All you have to do is that solve these equations, find out final momentum, and based on that you can find out final velocity. This is a solved problem from the book. So the way it works is that you have initial momentum here, force is applied, you take this force here, you solve this integration, and you can calculate final momentum, then you will get final velocity. So that's what we do here. Put the numbers in. Initial momentum, that's initial angular momentum of the car. 0 to 5 seconds, force applied for 5 seconds. That's my 150 t square force here, and then that will give me final momentum. So all you have to do is solve this simple integration here. 150 t square, it's simple. 150 goes out, t square is 2t. 0 to 5 seconds, apply the limits, and then once you do that, you'll get final velocity. In this case, that final velocity will come 9.17 meter per second. So you start with 5 meter per second, you end up with 9.17 meter per second, and that's the general idea. You have initial idea, you have force applied, find out final velocity, and that's how you can use this principle of angular impulse and momentum. This one is solved problem from the book. And then the final part of this chapter is steady flow of the fluid system. We can use this principle of linear impulse and momentum for these steady flow fluid systems. So let's assume that we have large pipe and then there is an opening. This is called a control volume. Control volume is open system. It means that mass and energy both can transfer the boundary of the system. So here what we have is large masses entering at some velocity, and then it's going to exit from this small opening. So here we have some velocity, but as it is a small opening, the velocity will be higher here. Some momentum here, mass into velocity, and then higher momentum here again, mass into velocity, as velocity is higher than this part. So what's going to happen is that momentum here is different. When it comes out, momentum is different. It means throughout the process, there will be forces generated at this joint. If I want to design this joint efficiently or effectively without breaking, let's say this large amount of water in under pressure, and if that's the case, the forces generated will be very high. And if you don't design this joint properly, this joint could fall apart. There could be a cracks, it could be fall apart, and this won't work. You don't want that. You don't want this joint to fail. So what you want is to find out forces on this joint. For that, you can use this principle of impulse and momentum. You have initial momentum, you know final momentum. Based on that, you can calculate this net force here, and once you can calculate net force, you can design the joint, and that's the idea. Now for that, what we do is, this is the equation. I am going to take this m1 v1 this side, and then I am going to rewrite this equation into this format. This is still same thing. Now if I rewrite this equation in same format, these forces will see that dm by dt Vb minus Va, or V2 minus V1. That's the same equation, that resultant external force. For this force, I can write this equation like this, and then I can use this equation to calculate this F. This dm by dt is nothing but mass flow rate, that how much amount of mass is flowing through the system, that how much amount of mass per unit time is going through the system. That's my mass flow rate. So if I know the mass flow rate, I should be able to find out the forces. So take the mass flow rate, put it here, get your final velocity, get your initial velocity, initial velocity here, final velocity here, put the numbers in and calculate that force. Now this one is a vector equation, therefore the forces will be in x and y direction, and in this case I want to find out reactionary forces in x and y direction. So I can resolve this equation into two components, x component and y component. So here I want to find out forces in x direction, I want to find out forces in y direction. So the velocities in x and y velocities based on the system, the way we have, and also it will have some rotational impact, some moment of force. So as it is going to have some rotational force or moment of force, I'm going to apply this equation here, and then dm by dt, this is again same format. This is the equation I'm going to use to get that moment of force here. So we can use this part, and then we can calculate this fx, fy and moment of force, and once we know the forces, we can design this joint properly. So in this problem, there is a problem in your book for practice problem. We are not going to solve this problem here, but you can do it at home. On page 298 of your book, there is a problem. In this problem, what it is, that there is a water is flowing at 100 kPa, very high pressure water is flowing through this system. The flow rate is given. Based on flow rate, you can calculate velocities. the density of water is given. We have to find out components of reaction at A, Fx, Fy and Fz. So this is my point A, or this is my surface A. At this surface, we want to find out forces X, force Y, M, moment of force. That's your reactionary forces to design this joint properly. Now to do this part, we are going to use this equation, principle of impulse and momentum. This equation is resolved into three components, X component, Y component, moment of force. You can use that and you can find out these reactionary forces. All you have to do is that go on page 298, understand this problem and solve it. It's very easy problem once you know how to use this equation and once you know altogether what's happening. This one is a solved problem from the book. And that's pretty much your chapter 15, impulse and momentum. And that's it. This is a small chapter, it's not a big chapter, but that's the end of this chapter. And that's it. If you have any questions, just email me, and that's pretty much it. I think these notes are already on Blackboard, and now this video is here. The next video I will post later will be of chapter 16, that's your kinematics of rigid body. Very interesting chapter. So let's stop here right now, and then I will see you in the next video for chapter 16. Stay safe.